Hello, and welcome back. You all are getting a 2-for-1 special today. Doing day 3, 2022. Let's get into it. So we have some elves carrying rucksacks that have 2 compartments. Our input is basically a list of lines with a jumble of letters. Um, and the compartments for part 1, you basically just split the string in half. So the first half will be one compartment and the second half will be a different compartment. Um, and then the idea is that you're supposed to find the one and only item type that appears in both compartments. And then you score those using some sort of priority measurement. So lowercase a through z have priorities 1 through 26, and uppercase a through z have priorities 27 through 52. Um, so the idea for part 1 at least is we're going to get a list of these lines, we split them in half, we find the character, the single character that's in common between both halves, and then we grade that character using this priority measurement, and we sum all of those priorities, and that'll give us our answer. Fair enough. Okay, so 3.txt1, this is our input. So I think it's helpful if we just, if we get everything into this, excuse me, if we get everything into this priority scoring to begin with. So one thing we can do is quad A again. Now quad A is the string containing all of the uppercase characters. If you do quad C, then you get all of the lowercase characters. This quad C is case change built in. And then if we put quad A on the end again, this is a list of all the characters lower and uppercase, and they're in the correct order for priority scoring. And we are in index origin 1 right now, so the index of any of the characters into this string will give us our priority scoring. So we can say, we can bind this to index for index of, and then we can say for each ingid, etc. And this will translate our input into the priority scores. And so we can assign this to P. Now, for part 1, we have to shift, we basically have to break our strings in half. The way that I would do this is by using the reshape operator. So we're not exactly sure how many columns there are going to be, but we want a 2 by x matrix. So we can do length W divided by 2. That's all of our lengths divided by 2. We can do 2 catenate to give us a list, and this is a nice input for the reshape function. So what this has done is we get this nested list of matrices where the first row is the first half and the second row is the second half. The nice thing about the input is that everything is going to be an even length, so everything splits evenly. And then we have to find the characters in common between the two halves. So with Dyalog, where is it? We get this intersection function. We have a bunch of set operators here. We have union, intersection, without, all sorts of stuff. Now, it would be nice, let's say that we take the first cell of this. It would be nice if we could just do intersect reduce first. So basically we're taking the first row, intersect with the second row. But the thing about reduce first is it doesn't actually operate on the major cells of its input. Reduce first only works for scalar functions for whatever reason. No one knows. So instead what we'll do here is we can split these matrices so that we get a vector containing 2 elements. Oh, this tokenization is skipped for long lines for performance reasons. I've never seen that before. Interesting. And then we can do intersect reduce to find the characters in common between these two halves. Now we get some of these have multiple characters, but there's only one character in each one. The problem input doesn't say anything about there being multiple instances of the same character. So we can just do for each first, and we get this nice flat vector, and if we sum it, we get 7,821, which is our answer. Part 2 says that basically we're not splitting the strings anymore. Instead, we are considering each group of 3 lines, and we have to find the character in common between each 3. And importantly, the groups of 3 that we're going to be considering don't overlap. So it'll be like the first group of 3, the second group of 3, etc., etc. So if we look at P, we can again do this with reshape, but now we don't have to do each, so we can do shape W, and this time we're going to be dividing by 3. And then we'll do 3 jot W like so. Actually, sorry. In this case, we want 3 columns, not 3 rows. So this gives us this matrix where you can see that it's a nested array, and we have 3 columns and some number of rows. And just like before, we can do intersect reduce across the rows, and for each one we can take the first one, and then we can sum them to get 2752, which is our answer. So 3-video.dialog. Yep. Okay, so this is part 2, and this is part 1, and we did some parsing of our input. Now we could stop here, but I thought, just looking at our solutions for part 1 and part 2, it looks like there's a significant amount of overlap. So we're calculating the shape, and then we're doing this intersect reduce for each first thing. So I thought it would be fun to kind of like break out those common elements, put them into their own functions, and then the part 1 and part 2 calculations are going to be a lot shorter. The intersect reduce for each first sum looks like it would be fairly easy to break up, but the problem here is that part of it is inside of this for each function. So if we can figure out how to break that out, so here for each P we have this is breaking each string into these 2-row matrices. Now we can mix this, and that's going to give us a rank 3 array, 300 by 2 by 24. And because in a matrix it has to have the same shape, the rows which have fewer characters have these zeros appended on the end. So now if we break this apart, we get this 2-column matrix, which is again nested. And now we can do intersect reduce. Now this gives us a bunch of zeros after the fact, which doesn't really impact our answer because we're going to be taking the first element anyway, and then we can sum, right? So we've managed to break out this intersect reduce for each first sum into its own component, which we're doing for part 2 as well. So if we have a function called g, which is sum for each first intersect reduce, now part 1 over here. Yeah, part 1 is just G with this part, and then part 2 is going to be G with this part. So we're starting to break apart the common elements here. So now we have this, and this is our new part 1, much shorter, and our new part 1, or new part 2. And if we run all of this, we should get the same answers. Okay, and with G broken out, we can see that like the inner operation here is very similar. So it would be nice to make this its own function as well. Something like, imagine we had a function f that on the left side it'll take the number of elements that you want to break apart, and then on the right half it'll take some input. So we could do like length w divided by alpha, concatenate alpha, and then do a reshape on w. And if we do this, then our part 1 answer suddenly becomes for each f2 because we're breaking things into 2 elements. And that gives us this answer. But the problem with part 2, the difference between part 1 and part 2 is that in part 1 we know how many rows we want, but we don't know how many columns we want. Because we're breaking things into 2 halves, so we want 2 rows, but we don't know the length of each string in advance, so the resulting matrices have a variable number of columns. And in part 2, we know how many columns we want. We want groups of 3, but we don't know how many rows there's going to be. So for part 2, if we just run f on p, we get and we're breaking it into 3 groups. Then we get this matrix, which has 3 rows, but has, a bunch of columns. And it would be nice if we could transpose this and then run G on it, right? Because if we transpose, we get a matrix with 3 columns. And if we run G, that's just our intersect, reduce, etc. But we get a totally different answer for this, 2519. And the reason is that when you do reshape, when you reshape something, it starts at the first index in the upper left of the matrix, and it starts putting together like it'll be the upper left element of the matrix, and then the one right next to it in the row, and then the one after that. And once all the rows are filled, then it goes back down and it starts filling out the next row. And when we did this transpose, basically each one of these rows is not like the first group of 3, the second group of 3, etc. It's like the first element plus, skip a bunch of elements, then 1, skip a bunch of elements, then 1. So we need some way to modify our function here, f, so that we can flip around this string that we're building to provide to reshape. Because in part 1, we know how many rows we want, but we don't know how many columns. And in part 2, we know how many columns we want, but not how many rows. So if f were like this, where we can just like flip this, then if we run this, not on transpose. Then if we run this, we get the right answer of 2752. So how can we extend this function to be able to take an argument to tell us like whether to flip this or not? We're already using both sides. These defends traditionally take 2 arguments, and we're using the left side to say how many times we want to split our input, and then our input is on the right. So we're sort of out of arguments. We could have like a list argument on the left, and then we can parse it inside the function, something like that. But something interesting that I thought would be cool to show off is the ability to build your own operators. Now, what's an operator, you ask? An operator is a function that takes other functions in order to modify its behavior. You can think of this like higher order functions or functional programming or whatever you want to call it. But like an example of an operator would be, say I have, a string from 1 to 10, and I want to use the at operator to say at the fourth element, I want the number 20, right? So what the at operator does is it takes a far right input and it takes this kind of like inner input to modify things. Then it takes a left argument here. So it's taking three inputs here, and it's running its function and coming up with its output. Another example might be like the key operator. So if I have if I have like a bunch of random numbers and I want to know the count of the different elements, then I might run the, well, count would be like this. Then the key operator takes an input on the right, but it takes an additional function on the left, and it's using that to modify its behavior. And the way that we do this in Dyalog is you can write your own operators, and you do that with a double alpha or double omega. And so if we write f in this way, now for part 2, we can supply a function that's going to be run on the list that we provide to reshape. And in this case, we want to flip it around so we can just use the reverse function, and we get the correct answer. For part 1, it's going to be, for part 1, we want to run for each f like this, and this right tack basically just means like keep the argument the way that it is, and then 2 because that's how we want to split it, and then we can do our mix split g to get our answer of 7821. Yeah, so I thought this was kind of cool because I don't often get to write my own operators, and this makes our 2 parts much shorter. This means that this is part 1, and this is part 2. So we've kind of abstracted all the common behavior between the 2 parts, and we're using an additional function to modify the behavior of to modify the behavior of the function that we're using to reshape our elements. And so if we run this, we should get the correct answers. So I thought this was kind of cool. I think that there are a ton of ways that you can do this problem, but I thought this is neat. And actually, if you want to get really trippy, you don't even have to have this space between all the alphas. It'll parse the first 2 first. So you could do this. This looks a little bit weird with 3 alphas in a row, but it does work. Yeah, so that's day 3. I thought it'd be fun to show off this operator functionality. It's not something that you see very often when you're writing your own functions, but it does allow you to sort of take advantage of like higher order functions or functional programming or whatever you want to call it. Okay, that is it for day 3. Thanks for tuning in.